All right, so in this module, I want to talk about factors that influence these thermal transitions, glass transition temperature, Tg, and the melting temperature, Tm. All right, so when we talk about the glass transition temperature, again, we're going from that glassy region, and the physical kind of meaning or scheme behind this is that in that glassy region, things are frozen, right? So the chains of the polymer are basically frozen in place and they can't move. So there's no long range chain motion. So Tg, or the glass transition temperature, basically is the onset of that motion. So chains are now have enough thermal energy for chains to move relative to one another. And so the values of Tg reflect the ease at which polymer chains can move in this way. So to so anything on the chains, the polymer chains or structure that inhibit chain motion or decrease flexibility will lead to increases in Tg. So basically, stopping things or preventing things or making it harder for chains to move increases the Tg. And so for things that do that, double bonds decrease flexibility, and so things can't move as easily. Electron-rich groups like ethers, ketones, and phenyl rings, all of those basically prevent motion. And also anything that's bulky, any bulky side groups will inhibit motion as well. So before we sort of get more into some examples, let's go and use that we just talked about and see for a vinyl polymer, right? So a carbon backbone, what side group listed below here, either hydrogen, CH3, or this ring, which one of those on a vinyl polymer would give it the greatest Tg? So go over to the quiz, if there is one for this week, and answer that. If not, just do it on a piece of paper and then come back and we will discuss. All right, so let's go ahead and look at the connection between vinyl polymers and their side groups and look at how that affects Tg. So on this next slide, we've got a list of various Rs, right? So the side group for a vinyl polymer. And we want to look at the Tg. So the simplest thing we can have is H, right? That would give us polyethylene if we plug that into here. And we see that that has a rather low temperature. Keep in mind this is Kelvin, so not Celsius or Fahrenheit. So this is rather low temperature. And then we have CH3. That's the next one here. And we've increased the temperature by 100. So we're close to room temperature. And then we start to see the complexity go up, right, like this, and we see it's even higher now. So now we're above room temperature. And also we can have things that are more electron rich, like Cl. So this is PVC. And then OH, also the same idea. We have those, and then a phenyl ring, which also is electron rich and also rather bulky, and that increases. So all of those things that we talked about in the previous slides, let me go back to that for a second, right? Double bonds, electron rich groups, bulky side groups, anything like that is going to increase the Tg of the material. And so here you just see some examples of how these affect the glass transition for a given material. So for the answer for that one, then it's the phenyl ring at 373 K. All right, so this is just kind of going back to what we saw before. Any of these things will affect the Tg. So anything that affects the motion or flexibility will have those effects on glass transition. And so the nice thing for us is that the same factors influencing Tg will also influence melting in much the same way, but melting is going to be higher. So any structural factors that influence Tg, like those side groups or that affect the flexibility, will also affect melting, right? Because we need flexibility and we need motion for the rearrangement into those materials. So will also increase the melting. And you kind of see that the ratio here for TG to TM is between 0.5 and 0.8 usually. So that kind of gives you an idea of how close they are to one another. And that's all in K. All right. So let's look at some melting temperatures for some common semicrystalline thermoplastics. So again, those thermoplastics are the ones that are reversible. So they can go from rubbery to solid and vice versa upon heating and cooling. So polypropylene is the lowest of this group at 170. So again, these polymers can't be used in really high temperatures. Um, polyacetal is 180. We have PET, which you're probably more familiar with, at 265. There's PBT, which is very similar there, 245. Nylons of various composition at 260 and 220. And then you have some others that are a little higher in temperature, going up to 340. So this is much higher. This is polyether ether ketone, or PEEK, and these have rather high temperatures. And you can imagine, if we look at the structures of these, those again, the ether groups were electron rich, and they might also have some double bonds and some bulky side groups that prevent flexibility and prevent melting. So the higher temperature that you see there.